Good afternoon, everyone in attendance. This is the we're Einstein Group Incorporated, and this is our design review 2 for the spring semester.
My name is Ryan Patterson. Anybody?
Tristan Youngblood.
And I'm Joshua Williams. So, a little bit of quote that we always like to say: strive for perfection in everything you do. Take the best that exists and make it better. When it does not exist, design it. And that was by Sir Frederick Fleming. That's it. So during this is going to be a pretty brief presentation today. We're going to mostly go present like the overview of what we worked on today, throughout this semester, but mostly the presentation will be based around the demonstration that we're planning on giving. Okay, so this presentation will include a need statement, an objective statement, the requirements and specifications, level 0, 1, 2, and 2 block diagram, a UML diagram, the test plan that we incorporated with our demonstration, the work breakdown that we worked with a Gantt chart to give a picturesque view of what we worked on and the cost, and we're going to demonstrate what we came to fruition with.
For the need statement, why is this needed? Why isn't this more popular than pros and cons of this project of this autonomous car? A couple pros are long distance. People want to travel a long distance without having to stop at hotels, rest stops, things of that nature. Want to go straight to their destination. People with disability that are not able to get around as much. This autonomous car would help it very much in that category, and also multitasking. As of now, texting and phone calling and things like that are illegal. Well, through autonomous cars, this can be very just taken away through that. Cons of this is usually cost. People are scared, especially the older people, are scared of new technology and electrical error. There's always electrical error in any technology. Objective statement. What we're trying to do, who we're working for, and how we're going to do this. Here what we're trying to do is make it a futuristic car actually not a futuristic car, it's actually being built now, and it is here now. But we're trying to establish it in the future so that it can be in process lines and be taken on a day-to-day basis, so we see it on a day-to-day basis. We're working for and with Texas Instruments in getting this toy car developed. What we're doing and how we're going to do this is we're going to implement an RC car where we take the concept of autonomous car, a real autonomous car, and put that technology into an RC car, showing its capabilities. A few engineering requirements and marketing requirements. For the engineering requirements, we have the ease of assembly and durability, which are some of the more key engineering requirements, which includes, for durability, includes the hardware and the outer shell of the RC car to make sure that it stays together, and ease of assembly. On the other side, if we want to really put it on a process level and really get it out to consumers, we want to be able to assemble it easily. And as a marketing requirement, the RC car would have a range of ability for anyone that can be able to play with it, or something of that nature, and it'll be user friendly. So everyone, no matter what age, will be able to enjoy this RC car.
So we're going to a little bit of the block diagram for our car. So basically, level 0 is the most basic level, and basically for what we have going on right now, which is we're controlling the car through our computer at the moment. What's going coming in is basically user input, and whatever is being sent in terms with our distances that we are planning on adding later on. And what's going to come out is the steering, speed, and direction it's going into, and where it's controlling the front wheel or the rear wheel. Going into the next block diagram, which is the level 1, it's going to go into a little bit more on how everything's being controlled. Basically, it's saying like we got the same inputs and same outputs, but now it's going into our base control station, where that's going to be saying, hey, I want you to do this, and it's going to look to, oh, I should do this. And it's going to send that to our wireless interface where it should say, it's going to connect to, it should connect to the car without being serially connected in the end. And basically from there it's going to move all the way through the local control and the motor control where it's going to make the wheels go in the direction it needs to go. And for those level 2 finally, basically this is just describing the more advanced layout of the local control unit, which is basically the logic within the control. And basically it's just saying, hey, we're getting in this data, what we're going to do with it. Let's check to make sure we're not satisfying a set of conditions, and while at the same time, let's see to make sure we're still connected with the hardware that we're trying to connect to. Then it just outputs the data that we need. And that's in the block diagram.
Alright, this here is the UML diagram of basically the entire system instead of doing one of the original function blocks like in level 2. From the user input, like you said, the user would actually turn on and connect to using the GUI to the actual vehicle. And then you would design the test path for this vehicle, and it would actually send the directions wirelessly. Right now it's not wireless, but through USB or serial connection. But the directions are sent, and then through the light sensor, which is also one of the inputs on the block diagram, it will go through, and then depending on what's actually fed back into the system, it would either change directions or continue on the path that was originally given. And after that, it would close out the program once the final destination is reached.
This is picked up from yours. This is picked up from yours.
Oh, they're just a UML? That would be addressed later. For testing of what we have so far, the test we got on the sheet that you have, the test, we're testing today with the
Test document?
the test document that you have. For today, we're testing the front wheel and the rear wheel capabilities, whether it be, move forward, move backwards, turn left, turn right, and where it stops in between each function. That's what we're testing for. And through our testing, we've been able to, send the instructions to the vehicle, but there have been a few issues between turning left and right, but the car does indeed move forward and backwards, given a certain speed. And that's the testing we have so far, given the parts that we have.
Okay, so briefly, I'm going to go over with you guys how we broke down each part of the car in order to complete it successfully. We each had our own goals in order to complete the car. My group member Henry had the challenge of creating a GUI controller and as well as programming it. Ryan and I both had the challenge of researching all the parts and all that, connecting all the parts together, and researching also how each part works and how each part is compatible with the other parts in the vehicle. And the last member in the group, Josh, had the challenge of researching the coding in the program in order to send to the motor controller and the Wi-Fi shield in order to function properly and do what it's supposed to do. Some of the problems that that arose from us doing our testing document that Henry already went over with you is that we weren't able to actually get it to connect Wi-Fi through MATLAB. We need to order more parts in order to get that part done. That's some of the things that we have to do for the future. And also that the Wi-Fi shield and the motor controller that we have ordered already wasn't compatible with each other. So that's another thing that we're going to have to order in the future. But we did end up connecting it serially in order to see if the programs that we already have with the MATLAB would work with the car that we have now. And like Henry said, it does move forward, it does move backward. We had a little bit of trouble with turning left and right, but that's something that we can efficiently, successfully complete in the next couple of days or the next couple of days. And then now I'm going to show you the Gantt chart, which is a physical picture of how we're going to break down each work. Right now, since we already built pretty much the whole car, as I told you before, we got to establish a wireless connection since we weren't able to do that as of right now. But from this part, we're just gonna be testing and troubleshooting the system of the car and seeing how we can perfect it.
So basically, going over the cost summary of the equipment we need. So basically, for right now, we have our Arduino Uno, a C motor shield, not naming a couple wires. Now we have it's called a XV, yes, XV. XV, it's called XV wireless communication, serial communication, and also we had a Wi-Fi shield, but we decided we're not going to use that with our. Well, we can use it, but we're going to have to come up with different alternatives. And that's the Wi-Fi shield. Oh, we did try to use the Wi-Fi shield, but the motor shield uses the same pins with the Wi-Fi shield. And what alternative we were going to try to do is, instead of using the motor shield, we were going to use the Arduino Uno and the Wi-Fi shield and connect the Arduino Uno to a dual H-bridge. We were looking at the series of the L293D and connect that with a 10 microfarad capacitor. And that would control both of the DC motors and dynamically, because originally we had a setup where we had the DC motor controlled, but they weren't controlled dynamically. We could just change it at a regular pace, or like up and down, like forward, backwards. It would just go forward, and it wouldn't change as quick as we need to, because like an H-bridge is good for making a dynamic change the direction and things like that. And what we have right now, what we had originally was we were using a NPN transistor and a 1N004 diode with a couple 330 ohm resistors, and we were putting them, I think it was like in parallel or series. Doing the series, and like it wasn't doing what we needed it to do. So we decided to go back with the motor controller, and this time we were going to use the XV's serial port wireless communication, and because it interfaces better with the motor controller and the Arduino Uno. And use that to connect with MATLAB, because what we found out with MATLAB, that when you're actually doing a wireless communication with it, it still needs to have a serial connection made, but XP can make a serial connection, but at the same time be used wirelessly to communicate with the unit that's connected to. But going back to the cost, right now we only spent up to $179 of our budget. We have a $500 budget, so we didn't go over, so we're good in that department. So right now, we're going into our demonstration. So, can you connect the thing to this talk here so we can show everybody the GUI and like that? I got it.
Because we was having a problem with the left and right turn. It was only turning a little bit because there wasn't enough power.
Okay, go ahead.
Okay, so now basically how this works is we have a code on our Arduino which makes it accept the serial communication going into it. And right now it's accepting a baud rate of close to 11,500 to 5,200. Alright, and
Through the USB.
yeah, through USB. When we go and use the XB communication, it's actually going to be less than that. It's going to be closer to about it's going to be less. I forgot the exact number. But pretty much, we got our GUI code in right now, and when we hit run, first I need to get rid of all this.
But you have a GUI panel.
Yes, we have a GUI panel. So when we hit run, right now it's saying attempting to connect. Right now it's trying to do a connection. Then when the connection comes, it's going to pop up the GUI.
Okay. But you may start from GUI and then click some connections, and inside of GUI you can connect it. And if you connected it in the blinking,
Yeah, that's it. And that's what we have here.
Yeah.
And that is what we're going to use, but instead of
you can hear some kind of green light.
Yes.
And red light.
Yeah, and the indicator on the motor controller also says that too as well.
Okay.
Okay, so hold on to that tightly. So first thing you want to check is make sure they go forward. So we're going to press up.
Yeah. This is go forward.
Yes.
Okay.
Then I'm going to stop it.
Stop. There. Okay.
Stop.
Stop.
Right. See that was front wheel turn, and this is
Oh
going
no.
slow.
Only right means that this only, not that one, this one is gonna move.
Well, we
Like
wanted to
this.
move at the same time so that we could, so there's more power going through this and less power going through this, so it can actually turn.
Oh, so you're,
So we,
okay,
yeah,
both
Yeah.
of them.
yeah,
Yeah.
so now when
And
it
then
goes left,
left.
see, so
Right.
it's-
This working,
Right.
right is working.
See, like, when you look
As
at
you
it,
can
right,
see, the right wheel is spinning a lot faster than the left wheel, and it's also turning to the left.
it's turning.
Oh.
Then I stop. Then I can, if
No,
I,
no, okay, this case is, you don't have to do that.
Mhm.
This is just, so you may change it to left and right. No, I don't think so. You have only one motor.
yeah, it's only one motor. Basically, I can
Right.
make it go forward or backwards. And I want to make this turn so that when it's turning, it can just turn in that direction that I have
Right.
it going in. And if everything's going bad, like let's say if I had to stop it and I want to just disconnect it and make it not do anything, it
Okay.
just disconnect. Then I hit connect. It shows the errors, but it's still good. And it just goes. It's down, right?
It's faster than,
Yeah. Then stop.
Okay.
And it goes back into its original state.
hmm.
And to make, we're going to plan on using these XBs wireless interface. We just got these in today. We're going to combine these with our motor shield and Arduino Uno and combine it with our computer so that we can have our wireless communication going through. Then from there, to make it run autonomously, we know these distance sensors that TI has. They're called the PIPO, I believe they're called, sensors, and we can use that to actually have it run autonomously because it can check the distances. And we're going to have it at the back, sides, and the front to make sure that it's not going to hit a wall. It knows when to stop and keep going and everything like that. And like we want to finish it by actually having it create its own path to its own destination. That's our highest goal. So let's go to our conclusion.
This doesn't come to the, this must come to the center. But this doesn't come to the center.
Return
Oh,
back to the
right now it's on, so it's not gonna. You gotta literally disconnect it to make it go back. Like
So
because-
return to a neutral position.
back to the-
yeah, because when it's on, you can't really do anything to it.
I think you need a lot of errors in it because, you know, if you run it and like this, then it's continuously like this. But left is left and goes straight, right? You see, if it is left and go straight, then it's gonna. This guy is, right center. You know, if it is this one, it's continuous rotation, continuous rotation.
Yeah,
But
until you change it.
if you left means that left and go.
Yes,
Go
we're looking
straight.
for.
For the
So
basis
you
of
need
it-
a lot of algorithm to control right away.
Yeah, but our basic controls were just to make sure that we went left or right, and then while simultaneously with the rear motor. So.
You start it, right?
Yes, sir.
But if you start it, this might be center. But even though you start, this, look at this. This is for left right now.
Well, so apparently with the wheels, like they don't go perfectly stop to the center, but like
Yeah, that's what I'm saying. It's like that. See, this is all the way right, so that's straight, but then this is already left. So it's like it's almost off a little bit.
It's because of calibration there, right?
yeah,
Okay, yeah,
we gotta
yeah.
work on it.
I'm sorry.
That's fine.
You need to calibrate with this one.
Okay.
Yeah.
With this.
Oh, okay.
This is the calibration.
Okay.
So at the beginning you can.
So that's what we're off at.
Okay. And so to conclude, we believe that Thomas Carter, the future of society, the technology is here, engineers are ready, and that the world is calling for a safe, efficient, eco-friendly, financially acceptable self-aware toy car. We at EGI hope that we can fulfill our consumers' need and hope that you're on board with our progress to the next level of engineering and technology. Thank you.